All right, let's take a look at this warm up here. So, a report for the National Center of Health Statistics says that the height of a 20-year-old man chosen at random is a random variable h with a mean of 5.8 feet and a standard deviation of 2.4 feet. Find the mean and standard deviation of the height j of a randomly selected 20-year-old man in inches. So basically, we're going from feet to inches, which means we're effectively multiplying by 12. All right. And if we're multiplying by a constant, that's going to affect both the mean and the standard deviation. All right. Both of those are affected when we're multiplying by a constant. If we were adding or subtracting a constant, it would have only been the mean, but this one's both. So we're basically just going to do the 5.8 times 12, and we're going to do the 0.24 times 12 and get our new values. So 5.8 times 12, 69.6. 0.24 times 12, 2.88. All right, so those would be our new means and standard deviations, again, because we're multiplying by a constant. All right, New Hampshire, Maine, and Vermont share a lottery game. You choose a number with 3 digits. The state chooses a 3-digit winning number and pays you $500 if your number is chosen. Taking X to be the amount your ticket pays, the probability distribution of X is as follows. So you have a 99.9% chance of getting nothing at all. You have a 0.001 chance of getting $500. So we're going to start by finding the mean and the standard deviation. Now, the mean you could very easily do just by saying 0 times 0.99 plus 500 times 0.01. But considering we have to find the standard deviation, we're going to have to put it in the calculator anyways. So if you go to stat edit, there's my 0 and 500. And then there's my 0.99 and 0.01 there. All right. All right. Hopefully that's a little clearer now. So if I go to stat calc, one variable stats, just make sure the frequency list is L2, hit enter. All right, my expected value is 0.5. My standard deviation is 15 point, we'll say 80. We'll just go with 80. All right, so 15.80, where this was 0.5. Now, if you buy a pick 3 ticket, your winnings are actually X minus 1 because it costs $1 to play. So find the mean and standard deviation of W. So here we are subtracting a 1. And when we subtract a constant, it only affects the mean. All right, so our standard deviation is going to stay exactly the same. All right, this has 0 impact on our standard deviation. It stays 15.80. However, our mean does get that transformation, so it's going to be 0.5 minus 1, which changes it from a positive 0.5 to a negative 0.5. So this would be our new mean right here. All right, so the standard deviation stays the same. The mean, that transformation does occur, and we have to subtract 1 from it. All right. Number 3, when making stats assignments, there are non-word errors and word errors. Not that I ever make mistakes. A non-word error is not a real word, such as when the is typed as te. A word error is a real word, but not the right word, as when lose is typed loose. The mean number of non-word errors is 2.1 with a standard deviation of 1.136. The mean number of word errors is 1.0 with a standard deviation of 1.0. Find the mean and standard deviation of W, where W equals Y minus X. So here we are combining random variables. The expected value of W is just going to be the expected value of Y minus the expected value of X, which in our case, Y had a mean of 1, X had a mean of 2.1. So our new expected value is going to be negative 1.1. Now, the standard deviation of W is a little trickier because you can't just add the standard deviations. You have to add the variances and then turn it back into a standard deviation. So it's basically like we're taking the 1.136 and squaring it, because that's a variance. We're adding it to the 1 squared, again, to turn it into a variance. That allows us to add them. And then after we add them, we're going to take the square root to turn it back into a standard deviation. And I kind of like to say it sort of reminds you of Pythagorean theorem. Right? It kind of looks like that a squared plus b squared calculation you used to do. So 1.136 squared plus 1 squared is 2.29, we'll say 05. 2.2905. And then it says, what is the probability that a randomly selected assignment will have more word errors than non-word errors? So basically they're saying, what's the probability that W is greater than or equal to 0? Because remember, W is just subtracting these two things. So we're saying, what are the odds you'll have more word errors, which is Y, than non-word errors, which is X? So we're basically saying, what's the probability that W is going to be greater than or equal to 0? So this is where we use our answers from up here and place them in our NCDF. So we're saying, all right, what percentage are going to be greater than 0? So 0 is our minimum value. 9999 is our upper value when the mean is negative 1.1 and the standard deviation is 2.2905. All right, so bring over our calculator, NCDF, from 0 to 99999, negative 1.1, 2.2905. All right, and we get 0.3155, so about 32% or so, 32%. All right, so again, it's finding the new mean and standard deviation up here, and then using those values as part of an NCDF calculation in the second part of it. So let's take a look at the back. Sweet Valley High has the best swimming team in the region. Of course they do. The 400-meter relay team is undefeated this year. Each swimmer swims 100 meters. The times in seconds are listed right here, along with their standard deviation. All right. So assuming that each swimmer's individual times are independent, find the probability that the total time is less than 220. So we're going to start by creating a new random variable that's just these 4 swimmers added together. So the expected value of V is just going to be the 55.2 plus the 58.0 plus the 56.3 plus the 54.7. We're just taking all of those and adding them together. 55.2 plus 58 plus 56.3 plus 54.7. So that gives us 224.2. So if everyone swims to their average ability, they're not going to get it. But you don't always swim to your average abilities. Sometimes you're a little slower, sometimes you're a little faster. So what are the odds that they can actually get under what I presume is the school record of 220? Well, we're going to need the standard deviation of V to answer that question. And we don't just add these, we add the variances. So 2.8 squared plus 3.0 squared plus 2.6 squared plus 2.7 squared. That's us adding the variances, and then we're going to take the square root to turn it back into a standard deviation. So 2.8 squared plus 3 squared plus 2.6 squared plus 2.7 squared. So that would be the new variance. We want the standard deviation, so we're going to take the square root of that, and we're going to get 5.56. So there's the standard deviation for the entire team, not just one athlete, but the entire team of 4 people. And now we can use this inside of our NCDF to say, all right, what's the odds of ending up below 220? You might be saying to yourself, why are you doing negative? Like, you can't go below 0 seconds. Well, it's kind of irrelevant. Like, once we get far enough away from our mean anyways, the probabilities are so small, you're not going to notice. So it's fine to just keep using negative 999 there when the mean is 224.2 and this team standard deviation is 5.56. So if we go to our NCDF, we type in negative 9999, 220, when our average is 224.2, but we have a standard deviation of 5.56. All right. So, you know, they've got a decent chance of getting below that time. All right. Almost 1 in 4 chance, not quite 1 in 4, somewhere between 1 in 5 and 1 in 4 chance of getting under 220 seconds. All right, last one here. Leona and Fred love Statistics Club. They are both about to take a test and agree that if one of them scores 5 or more points better than the other, the loser has to give the winner $20. Assume that each of them has the same ability so that their scores vary normally with a mean of 84 and a standard deviation of 7. Their scores are independent. So what is the probability that their scores differ by 5 or more in either direction? So x minus y greater than or equal to 5 basically means that, let's just say Leona scored 5 better than Fred. X minus y less than or equal to negative 5 means that Fred scored 5 better than Leona. All right, so if we want to know this expected value of x minus y, it's the expected value of x minus the expected value of y. And sometimes these give students problems, but they both have the same expected value. So it's just 84 minus 84 or 0, right? We expect them to score about the same, so the expected difference is 0. And I think sometimes getting 0 makes kids nervous, but the expected difference is 0. So the standard deviation of x minus y, all right, this is where we're going to do the variances. Again, they have the same standard deviation, so it's just 7 squared plus 7 squared, and then we're going to take the square root of that. So 49 plus 49, or the square root of 98, and that gives us, we'll say 9.8995. 9.8995. So now that we have these questions, we can answer our NCDFs. We can say, all right, what are the odds of being 5 or higher when the mean is 0 and the standard deviation is 9.8995? And what is the probability of being below -5. Now, because the normal distribution is symmetric, we're actually going to get the same answer for both of these. So we could have just done 1 and multiplied it by 2, but I'll prove to you that we are going to get the same answer. So normal CDF, 5 to 9999 when the mean is 0. Oops, hit the wrong button there. When the mean is 0 and the standard deviation is 9.8995. All right, so we've got a 30, let's say 0.3068. And then if we flip this around and do -999 to -5, we're going to get the same exact thing. All right, so 0.3068. So when it says, what is the probability that their scores differ by 5 or more in either direction? All right, we're taking those two and we're adding them together. Or I can just take this answer right here and multiply it by 2, and you're getting the 6135. All right, if you just add these two together, you're going to get 36. Again, that's just a rounding difference versus if you're using the full exact. I'm not going to nitpick one way or another. So if you get this, or if you get this, either one of those is totally fine. All right, it's just a rounding issue. So again, combining the random variables, getting a new mean, getting a new standard deviation, using those values inside of NCDF to then calculate some sort of probability or percentage. But that's what a lot of these problems are going to be over and over and over again. So if you have any questions, make sure you ask. Otherwise, I'll see you when I see you. Bye.